Welcome to another episode of CCSD Earth Science. Today we're going to be talking about radioactive decay. Radioactive decay is a way that we're able to get an absolute or an actual age for a rock or a fossil. Until now, we've been looking at relative age dating, where we compare rocks to one another based on their sequence and order within an outcrop. But with radioactive decay, we're actually able to find a specific age, and there's a certain technique to that. Now, we're able to do that using something called a radioactive isotope. And a radioactive isotope is unstable, so it starts to decay or break down or turn into something else, a stable element. So the unstable element we call the parent element, and that decays into the stable isotope called the decay product or the daughter product. So parents or daughters come from their parents, and so that's a way to remember that as well. The decay process occurs at a constant rate. So as these unstable isotopes are starting to decay, it's a constant process. So it's predictable, which is why we're able to use it. Another really important thing about radioactive decay is that outside forces don't influence it. So a rock could be weathered, it could be broken down into smaller pieces, and the decay rate is still the same. So you think about all of the things that the Earth goes through and all of the rocks on the surface go through, they're able to maintain that same decay rate and allow us to get an age for the rock. The other thing about radioactive decay is that depending on the isotope you have, the decay rate is different. So different unstable isotopes or radioactive isotopes are going to have different decay rates, and that allows us to find ages of different types of rocks, rocks that might be really, really old or rocks that are maybe a little bit more recent. Now, one thing that we talk about a lot with radioactive decay is something called the half-life. And the half-life is the amount of time for half of the radioactive isotope to decay into the daughter product or the decay product. So if we look right here, this is an example. If you have a rock with carbon-14 in it, and the rock just formed and it's got all of the carbon-14 in it that it started with, over one half-life, you're going to see that half of the carbon has decayed into nitrogen-14. So the decay product of carbon-14 is nitrogen-14. So after one half-life, half remains. And that continues. So every half-life, half will continue to decay of what's left of the carbon-14. So you're going to end up with an increasing amount of your decay product. Now, the amount of time, that is what is dependent on what the isotope is. So for carbon-14, the half-life is 5,700 years, and that is just for carbon-14. We're going to look at some other isotopes, and there are some other isotopes on the cover of your reference table, and we'll be using those throughout the rest of this unit. So we talked about you have a rock, and say you start off with all of the parent element that's in that rock. So in this case, we could say 8 grams. We could measure how many grams of that particular element are in there. After one half-life, half of the parent isotope has decayed. So now we have 4 of the parent and 4 of the daughter. That's after one half-life. If we go through 2 half-lives, you're going to see that the 4 grams that we had to start with have now decayed even more by half into 2 grams. And the amount of the daughter product is increasing. It's gone up to 6. All right, so if we see that written out right here as well, you start off with 8, it goes by half, and then it gets cut in half again after another half-life. And throughout that time, you're going to see that the daughter product in the beginning, there isn't any of it here. It's all that parent isotope. But as time goes on, you're going to see that it starts to increase. Okay? And so we can look at that relationship and get an idea of the age of a rock. So we'll take a look at carbon-14. This is a very common isotope that is used to find ages. Carbon-14, its half-life is 5.7 times 10 to the third, or 5,700 years. And the thing about carbon-14 is it has a very small or a short half-life. So it's really good for finding the age of younger things. Now when I say younger, 40 to 50,000 years old. When we think about the entire time span of Earth's history, 40 to 50,000 years is not very long at all. And we'll go through and take a look at why it's good for that range. So if we start off with a rock that has all of its carbon-14, it goes through one half-life. The half-life, like I said earlier, of carbon-14 is 5,700 years. So if you find a rock and you measure the amount of carbon-14 and the nitrogen-14, and you see that it's half and half, that's telling you it's gone through one half-life and its age is 5,700 years old. If it goes through two half-lives, that half of the carbon-14 that we had is going to get cut in half again. So half of a half is a fourth. So we're just doubling that bottom number in the fraction. So if you find a fourth of the carbon-14 remaining, that's telling you it's gone through two half-lives and its age is 11,400 years. And it just continues on. So 3 half-lives, you're going to have 1/8 remaining. You go on to 4 half-lives and the age is right there. You're going to have 1/16 remaining. 5 half-lives, 1/32. 6 half-lives, you're going to have 1/64. The amount there is so small that really beyond this point, you don't want to use carbon-14. There's not enough left to measure. So when you find a rock that gets into that beyond 50,000 years old, there's so little carbon left that it's just not an accurate way to find the age. So we would use a different isotope. But when we're looking at some of these younger ages, it's great. It works out perfectly. Okay. Now one thing you have to keep in mind is the rock itself is not changing. This is all happening inside of the rock. The rock stays the same. All right. And this is just something going on within the rock that we can't see. Now another isotope that we use a lot is potassium-40. And potassium-40 has a half-life of 1.3 times 10 to the 9 or 1.3 billion years. So again, watching this process here, we've got 100% potassium-40 in this brand new rock. Okay, it goes through one half-life. That means that after 1.3 billion years, half of that potassium-40 has decayed, and it decays into argon-40. So this is significantly longer than the half-life of carbon-14. Carbon-14 was only 5,700 years. This is 1.3 billion years. So that's a good portion of Earth's history. We go right through, okay, so you go through 2 half-lives, now it's 2.6 billion. You've got a fourth remaining. 3 half-lives, you've got an eighth remaining. 4 half-lives, you've got 1/16 remaining. And within 4 half-lives of potassium-40, we're beyond the age of the Earth. All right, so you're not going to find anything on Earth that has potassium-40 that's gone through 4 half-lives yet, because the Earth is only 4.6 billion years. So we're somewhere in the middle after 3 half-lives, working on the 4th half-life right now. These last two are 2 other radioactive isotopes that are, again, on the front cover of your reference table. Uranium-238 has a half-life of 4.5 times 10 to the 9th, or 4.5 billion years. So if we think about the Earth, we just said its age is 4.6 billion years. So basically, uranium-238, any rocks that contain that were around at the beginning of Earth's formation, have only gone through 1 half-life. And there may not even be rocks that are that old that contain uranium-238, but because its half-life is so long, we really aren't going to find many rocks that have gone through 1 half-life that contain uranium-238. Uranium-238, that decays into lead-206. And so right here you can see that we're still kind of working on the second half-life of uranium-238 on Earth. And then we've got rubidium-87, and that's half-life is 4.9 times 10 to the 10th, or 49 billion years. So there is nothing on the Earth, there is nothing in our universe that has gone through one half-life that contains rubidium-87. It's just too long. So we really don't use that much for things on Earth because nothing has gone through that half-life yet. So we use uranium-238 more for things that are really old on Earth, or even for things if we're starting to find the ages of objects that were from outside of our solar system even. So radioactive decay, I'm just going to bring back that first board real quick just to kind of recap here. The big things with it, okay, is that you've got a parent element that's decaying and breaking down into your daughter element or your decay product. And like I said before, it's a constant rate. It's predictable. Nothing influences it other than time. Nothing will change how much of your daughter element you have or your parent element other than the amount of time that has gone by. Outside forces, pressure, heat, all those things that the Earth has gone through have not influenced the decay rate, which has been a huge help because it's allowed us to use this and allow it to be successful in finding the actual age of rocks. And by finding these actual ages, we've been able to create a much more detailed geologic timeline than what we had in the past.